Hello and welcome back to another IB Math Speedrun with me, Vince. So in today's speedrun, we're going to be going through the final part of chapter 10.3, which is about using trigonometric formula with the polar form of a complex number to find some interesting proofs. So let's jump right in. So the two important things we need to know is, first of all, if we raise a complex number z to the n plus 1 over z to the n, this is equal to 2 cosine n times theta. And the second thing we need to know is if we subtract the reciprocal instead, this is equal to 2i times sine n theta. So of course we can prove this, and n is natural and theta is real. And so this makes for some very interesting proofs. For example, we want to prove the double angle theorem. So if we square this, say z plus 1 over z squared is equal to z squared plus 2, I think it's plus 2, yep, plus 1 over z squared. And so the thing to note is, okay, if we substitute n as 1, we get 2 cosine theta, so this is equal to 2 cosine theta squared is equal to, and then if we square this, we have 2 cosine 2 theta. Since we substitute n as 2, we have 2 cosine 2 theta plus 2. So what we get is, we get that 4 cosine squared, theta is equal to 2 cosine 2 theta plus 2. And so we divide everything by 2, we get cosine 2 theta is equal to 2 cosine squared theta plus minus 1. So yeah, that's how we can prove the double angle formula using complex numbers. So let's jump into some questions regarding that. So first, we need to use mathematical induction to find, okay, fine. No, I want to do the even ones. So we need to let z is equal to cosine theta plus I sine theta. So first, we need to use the binomial theorem to find the real and imaginary part of z to the 4. Next, we need to use de Moivre's theorem to find the formulae for, so first we need to find cosine 4 theta and sine 4 theta. And then hence show that tangent of 4 alpha is equal to 4 tan alpha minus 4 tan cubed alpha divided by 1 minus 6 tan squared alpha plus tangent to the 4 of alpha. Okay, so first find real and imaginary parts of z to the 4. So z to the 4 is equal to it's equal to CS 4 theta. Oh, sorry, no, that's de Moivre's. We actually need to binomial this one. So by binomialing, we get, this is cosine theta plus I sine theta to the 4, which is equal to, if we square this internal part, this is equal to cosine squared theta plus 2 cosine theta I sine theta minus sine squared theta squared, which is equal to cosine to the 4 theta. Wait, no, I've just made it harder. Let's just properly binomial expand this. Cosine 4 theta. Next, plus 4 cosine cube theta I sine theta minus 6 cosine squared theta sine squared theta, since we have negative I, minus 4 cosine theta I sine theta plus sine to the 4 theta. Okay, so we need to use De Moivre's theorem to find the formula for cosine 4 theta and sine 4 theta. So we know this was all equal to CIS 4 theta. So this is equal to cosine 4 theta plus I sine 4 theta. And so we can find both of these by equating real and imaginary parts. So cosine 4 theta is equal to, 4 theta, big 4, is equal to cosine to the power of 4 theta minus 6 cosine squared theta sine squared theta plus sine to the 4 theta. And then, so, can we simplify this? I guess we can simplify it. I just wonder what form the book wants it in. Nope, that's fine. Okay, so next, sine to the 4 theta is equal to 4 cosine cube theta sine theta, since you can remove the I, since we know these are both imaginary, minus 4 cosine theta sine cube theta. Okay, and so next we need to find tan 4 theta. So we know this is equal to sine over cosine, so this is going to be 4 cosine cube theta sine theta, I guess alpha, but I'll just use theta, minus 4 cosine theta sine cube theta, all over cosine to the 4 theta minus 6 cosine squared theta sine squared theta plus sine to the 4 theta. And so the strategy is here we need to divide everything by cosine to the 4 theta. So that leaves us with 4 tan theta, since this is sine theta over cosine theta, minus 4 tan cube theta, since this is sine cubed over cosine cubed, divided by, and this is 1, since cosine to the 4 over cosine to the 4, minus 6 cosine squared theta plus tangent to the 4 theta. So that's why this is correct. Okay, and on to the last question. So given that W is not equal to plus or minus 1, but it's still a solution to z to the 6 minus 1 is equal to 0, we need to show that 1 plus W squared, omega squared plus omega to the 4 is equal to 0, and evaluate 1 plus omega to the 102 plus omega to the 1004 plus omega to the 20,008. Oh, but if they want the specific one, we can just use the fact that this is equal to z squared cube minus 1, which we can factor out into z squared minus 1 times z to the 4 plus z squared plus 1 is equal to 0. So since omega is not equal to plus or minus 1, which are the solutions to this, it must be a solution of this. So that's why. That's the answer. And so now we must evaluate 1 plus omega to the 102 plus omega to the 1004 plus omega to the 20,008 What pattern do we have here? I guess we could just solve for omega. Would that be the easiest solution? It might be, actually. So let's try that. Let's just solve for omega. So we have omega is the solution of this. Z to the 4 plus z squared plus 1 equals 0. Okay, are these all factorable by 6? So we have 1 plus 102 divided by 6, 17. So this is double omega to the 6 to the 17 plus 1004 divided by 6. No, that's not divisible. So we can write this as, what's the closest multiple? 1002 divided by 6. Omega to the 6 to the 167 times omega squared plus, oh, and I bet this is 20,008 divided by 6. It's not. Yeah, so this is, we can rewrite this as 20,002 divided by 6. So, 20,004 divided by 6. So this is w to the 6 times 3334 times w to the 4. And so the trick is, this is equal to 1, this is equal to 1, and this is equal to 1, right? So we just have 1 plus 1 plus w squared plus omega to the 4. And so the thing is, we know that 1 plus omega squared plus omega to the 4 is equal to 0 because of this. So the answer is just that, it's just 1. This evaluates to 1. So yeah, that was pretty interesting. That was all for the speedrun. I hope you enjoyed, and I hope to see you in the next one. So see you then.